today we're going to look at a very simple reaction for you to understand the concept of Hess's law and why we use it. So just like when I introduced exothermic and endothermic reactions, I use copper 2 sulphate anhydrous, which means it's a very pale colour. You can see that it's been sitting in my lab for a few minutes and already it's started to have blue tinges on the outside, which means it's starting to absorb that moisture. And then I have the copper sulphate pentahydrate, which you can see is a darker blue colour because that water has actually joined to be part of that compound. Now the purpose of today's experiment is we're going to go through and we're going to calculate the delta H for this reaction. The problem with some of our chemical reactions that we have in chemistry is that we can't often directly solve for delta H. And there's a variety of reasons why that is so, but for this particular example, it's because we can't directly measure the enthalpy produced from if we were to remove the water out of the substance or if we were to go vice versa. So we just basically can't do that. So Hess's law enables us to work with reactions where we can't directly solve the delta H. So you can see down here on my little diagram here that I've actually shown you that we are looking to and aiming to solve delta H3, which is a direct route to finding out the enthalpy change for our hydrated copper 2 sulphate. But remember I said we can't directly perform that. So what we're going to do instead is we're going to find an alternative route to be able to solve delta H3. And this is how we're going to do it. We're going to go through and take our anhydrous copper 2 sulphate, we're going to dissolve it in water, and we're going to record the temperature change. We're then going to do the same sort of procedure for hydrated copper 2 sulphate, dissolve it in water, and take the temperature change. Now there's a variety of calculations that we need to do in order to be able to get our final value for delta H. And obviously with Hess's law, we have to think about if there's coefficients in our reaction or if we need to reverse it. So I will take you through and show you how to do that once we perform the experiment, and Mr. Audie is going to be my lab assistant today and demonstrate to you how to use our Vernier DataQuest, basically our temperature device. So we're just going to perform the experiment, and I'm going to move you across to our scales here. And you can actually see, if I was weighing, it says in your instructions for this particular lab that you need approximately 5 grams or around about 7.8 grams. I didn't quite get that, but that's okay. On my weighing paper, I've actually gone through and I've written the exact amount that I've weighed, except I didn't do it on this one. It should be 7.79 grams on this. Now you can see I haven't been a particularly good scientist because I've been in a hurry and there's a little bit of error that's going to be on the side. You can see I've got a little bit of solute. We shouldn't aim to do that in class. We should always be really perfect with when we weigh it because we want to minimize our errors. Now, Mr. Audie, what he's going to do, we've got 50 mils here in this beaker, and he's going to, oh, he's already got the beaker. He's going to pour it into our coffee calorimeter cup. So pour the 50 mils into it. And he's going to take the initial temperature and he's going to talk a little bit about what he's going to do.
Yeah, so the polystyrene cup allows for some insulation so that we lose a minimum amount of heat to the environment. And what we're doing here is you can see that we're measuring the initial temperature. So we have to wait for a few minutes for it to settle down. And it seems to have settled at 25.9.
Okay, great.
So we're going to record that.
25.9 degrees Celsius, and we're going to pop that down, okay?
And what we'll do is now add the anhydrous. So because we know both the weight, the mass of the salt, and notice it's white, but when we add it in here, you're going to see that it instantaneously turns blue because it's formed the hydrated salt. And we will measure it, stir it, and if you see that the temperature is rising because it's an exothermic reaction. So you just need to wait a couple of minutes to see if it stabilises at that. I'll give it another stir, but I think that seems to be stabilising. Yes, so it's stabilised at 33.2.
Okay. Okay. Right.
Now we'll repeat the experiment, but with the hydrated salt. So again, we need to get the initial temperature, which will take a little minute to drop back down. To air temperature, which was 25.9, so let's just wait to see if until it reaches air temperature. Yeah, so there's 25.9.
Okay, let's write that down on the table. So it's 25.9?
And now it's dropped to 25.7. So now we're adding this is the hydrated salt, which is 7.79 grams of that. And you can see that this is actually an endothermic reaction, that the temperature has dropped. So it's requiring energy to dissolve this because copper sulphate was already with water. It already had the water of hydration.
Okay. So while I'm actually stirring this and just waiting for a few minutes, what is your most important message for those students that are going through to take AP Chemistry next year about bond breaking and bond forming?
Yeah,
Famous for it, Mr.
well,
Ray.
when you're dealing with a chemical reaction like this, and both bonds are being broken and new bonds are being formed. Whenever a bond is being broken, that requires energy. And whenever a new bond is being formed, it releases energy, it's exothermic. So what happens is that in each of these, you've got bonds breaking and then new bonds forming. So because this one was exothermic, it means that there were more bonds forming than there were being broken. Whereas with this one, is because it's endothermic, it means that the bonds already existing had to be broken, and that required more energy than the energy that was released when it dissolved with the water. So bond breaking always requires energy, bond formation always releases energy, but the overall reaction in this case is exothermic, in this case is endothermic, so you don't know until you actually do the reaction.
Okay, so we
got a final temperature of 23.6. So that has dropped more than 2 degrees.
Okay, so here's our final table of results, and I'm going to get back to you with part 2 where I go through and perform the calculations step by step for you.